Lesson 4.4 is going to show you the first derivative test, possibly one of the most important concepts of the year. We wrap up all of the understanding that we have about functions, derivatives, and we are now able to work on applications of what derivatives mean in the real world. So the first derivative test, there's a process here, and I definitely want to follow it. But before I get to it, I just wanted to, off to the side here, take note of common student misconceptions about increasing, decreasing, positive, and negative functions. Okay, so real quick, let me go over it. Here is a graph, just a basic graph. I have a graph that is, how do I say this? I'm going to make it have endpoints so that we don't have to talk about end behavior. I'm looking at my red function and I'm saying this entire function, f of x, is greater than 0. And what does that mean that I say that? Well, f of x is an output value, and greater than 0 means that they are all positive. All right, so that function is entirely positive. All y values, I guess I could put a dash here, values are positive numbers. Okay, then if I went down here and I said I had, some kind of function down here, again with endpoints, so I don't have to talk about where is the function going at infinity or anything like that. I say, well, what is this? Well, this is going to be f of x is less than 0, meaning all outputs are negative. And why am I talking about this? Well, if a function is positive, it isn't really necessarily interesting to me without some sort of context. Is that function positive? Is that function negative? The context that we're going to do is that in the first derivative test, I will check if a derivative is either positive or if the derivative is negative. But specifically, I'm going to check that derivative, okay? Which means I'm looking to see if f prime of x, you see me over here, I don't know if you just noticed, I put a mark right there. If my derivative is positive or if my derivative is negative, I will be able to say something about the original function, the function where the derivative came from. Okay, so if derivative, if f prime of x is greater than 0, I could say the original f of x is increasing. Why? Well, because the function, if I have a positive slope, then that means that the function is growing. If I have a negative slope, that means the function is decreasing. Well, I say it like this. Then f prime of x is decrease. But here's where we get to talking about these words increasing and decreasing. And notice what I end up finding as a teacher is that students get confused about that as well. So let's do another little graph right here. And I say that this is what things look like when they are getting bigger. And this is what things look like when they are getting smaller. Okay, so decreasing and increasing look like this. And notice that what I'm saying here is that increasing, it doesn't have anything to do with the y-axis, and it doesn't have anything to do at all with whether or not that value is positive or negative. What I'm saying is that the slope is positive here. So here, my increasing, I say that f prime of x is going to be bigger than 0 because, oops, I mean, I would love to be able to write this correctly. There we go. Is greater than 0 means that the function is increasing. Here, I say that if f prime of x is less than 0, then the function is decreasing. But notice that the function itself, I'm not telling you that the function is above the y-axis or below the y-axis. That is not something that I'm aware of when I say that the function is increasing or the function is decreasing. I'm only looking at the derivative at that point. I'm not necessarily looking at the outputs of the original function. So if you want to know where the original function is, we would have to be able to find it. Okay, so if we only have the derivative, we might need to maybe find, say, for example, the antiderivative, and then be able to say where that function actually lived on the y-axis. So once I take a derivative, remember that constants disappear. So that's how come I don't know where the original function lived on the y-axis. Was the function up here? Was it down there? Was it down there? I can't say, because the function, like say if this was y equals x squared plus 2, I would know that it was up here at 2. If this was just say y equals x squared, well, I'd say that it would definitely cross at the origin, right? If I was down here, say at -3, then I would know that the y-axis, there's a crossing there at -3. But because this disappears, I don't know exactly where that is. So I've lost the ability to say, where is y going to be positive or negative? That's something I don't know at this time. Okay, so I'm not going to be able to talk about that at this moment, but we're going to get to it. It's definitely on the list of things to do. So hopefully that'll orient you to, so what it is we're exactly doing is we are looking at whether or not the first derivative has positive numbers coming out of it. The second, and then the second check is to see where is it going to be negative and why, because is there a picture of it on here somewhere? I believe there is. So when we're looking for it, we'll see. I'll show you just a little bit more about increasing and decreasing intervals. Actually, let me just do a sketch right here. So he says, find domain restrictions, find those critical numbers, locate those critical numbers and domain restrictions on what he calls an F prime number line. And yes, you must label this. If you don't label it, they will not accept it as justification, and there are points given for justification. Test the sign. Test the sign, meaning is it positive or is it negative? And once we know, we can label those on the number line at those critical numbers, around those critical numbers. Listing increasing, decreasing intervals, identifying relative maxes and minimums should be pretty easy. Let's get to it. The frequent area of confusion for students is the question of whether or not to include endpoints on intervals. Some textbooks would say that my basic parabola is decreasing on a particular interval and increasing on the other interval. Others say that it is increasing or decreasing on these kind of intervals. Using closed intervals is not as intuitive, but it is more correct. The concept of increasing and decreasing is not based on a single point, but is instead about an interval. The pre-calc definition of increasing is that as x values increase, y values also increase, and that if this is true on an open interval, it is also true on the closed interval, as long as there is continuity. The College Board is well aware of this discrepancy among textbooks and has tried to make sure that students are not penalized. On a free response question, readers have been instructed to count either answer is correct. They will never list both open and closed options as multiple choice responses. It is more likely that multiple choice answers will be closed intervals. That's just what they usually do in multiple choice answers. So that question about whether or not to include 0 when listing where something is increasing is a completely separate question. All texts would say that it's increasing everywhere, even though the derivative is 0 at x equals 0. Any other answer would not receive credit on an AP test. All right, I took a moment to read all this because I wanted to make sure that you read it. Hopefully reading it out loud too makes it clear that we should know something about y equals x squared. And I'm telling you right here, I have that positive slope. Everything's going up here, and so I would want to say that it is increasing starting at when x equals 0 and going all the way to when x eventually approaches infinity. Okay, so I say that it is this. And we always use, by the way, we always use open-ended here on infinity because cannot get to infinity. And then right here, I say on this side that this, I can't get to negative infinity either, but I will be able to get to 0. And I'm telling you, my function is going down here. And you're like, well, again, Ms. Shatra, I'm not sure I understand what you mean. And so there's a little bit of the XY table that I find not helpful. At times I find it not helpful because let's say that a normal XY table, say I do this, right? I say 0, if I square 0, I get 0. If I square 1, I get 1. If I square 2, I get 4. If I square 3, I get 9. And we write it like this. But actually, intuitively, it makes more sense since this is 0, and that is 1, and that is 4, and that is 9 up there. It would make more sense if I said this: 3 and 2 and 1 and 0. Can you see how the y values are increasing? Do you see what I mean? It makes just a little bit more sense if I write it like that. Y values are definitely getting bigger over here. Now, interestingly enough, we say, if I'm talking about how like XY tables are kind of like written a little bit weirdly, like not intuitively, I could talk about this negative side as well. And I say, oh, well, here I had that table for 0, 0. And then what if I throw in a negative 1? I still get a positive 1. What if I throw in a negative 2? I still get a positive 4. What if I throw in a negative 3? I still get a positive 9. So is it, these are where numbers are more negative. So the more negative you get, the more positive I get. Does that, I don't know, is not really helpful. Here, let's try it again. So we say that as the numbers are getting more and more negative, the y values are getting more and more positive. So the function is decreasing. Wait a minute. Do you see what I mean? The numbers are decreasing here. Now, decreasing. All the way until I get to 0, right? All the way until I get to 0, the numbers are decreasing. And so as a final like thing that I would maybe do, and I'm not sure if this, I've never really presented it like this before, so you tell me if you like it, but -3, 9, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, 3, 9. The function is decreasing to get to here, and it is increasing to get to here. Oh, do you like that? I was hoping that you would. All right, just as far as when we're talking about XY tables and what it is you see. If you do feel like any of that helped you with understanding increasing and decreasing values, I'm very pleased. And so here then at the very bottom, this right here is so important. I do need to mention it to you. There's something called monotonic increasing functions, where you're going to see, and he does give us an example in here where the function is always increasing. It is never decreasing at all. And you're like, well, what do you mean? Well, let me take a look at here, Desmos. I have y equals x cubed, and so I'm saying that as you approach 0 from the negative values, look, the numbers are getting closer and closer to 0, right? The y values are increasing. Well, after 0, the y values are still increasing. I'm still growing. My function is going to be growing, it looks to me like forever. Okay, so that's x cubed, and that's what a strictly monotonic increasing function looks like. And if I do something to x cubed, like minus some value, it will make a moment where the function right here, I was heading up, and then boom, all of a sudden I am heading down again. And oh, wait a minute, that is when I'm going to start heading back up again. Now from here to here, extremely important moments in time where I want to know, when did this function change values? As in, it was increasing and then it was decreasing. And I'm very interested in that. But again, I might not be able to tell you exactly when that took, like whether or not the function was positive there or negative there if I don't have that original function. So like if that was a +3, then it would look like this, but if that's a -1, then it looks like that. And so I could see right here, this is where my function is positive, but I might not be able to find that right now. Okay, if I don't know how to undo the derivative, whatever derivative has been taken, if I don't have that original function. So those are the differences that we see, and I hope that you feel ready for this section now.